following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
We'll shift our focus now to resonance and electron dot structures. If we take a look here at figure 15, for ozone, if we follow the steps that we had just outlined in the previous slide, then we would end up with the following molecule for ozone just before we reach step 5. And at step 5, in order to complete the octet configuration for the central oxygen atom, we would need to take a lone pair from one of the terminal oxygen atoms, that being the one on the left or the right, and make it a double bond in order to complete that octet configuration, right? Now, which oxygen would we take it from? If we take it from the one from the right, then we would have this scenario. If we take it from the one from the left, we would have this scenario on the right. Well, the answer is actually going to be neither, right? Because anytime you have a valid electron, anytime you have more than one valid electron configuration, as we do here, the actual configuration is going to be an average of all the possible valid electron configurations, and that is known as what it says up here is the resonance hybrid. And let's go ahead and read that definition. A resonance hybrid is the average of several valid electron dot structures for a molecule. Now, for example, if we come back to the oxygen molecule for a moment, there's actually experimental evidence that both of the oxygen-oxygen bonds that we see here, they actually have identical lengths. Thus, there shouldn't be any side-to-side asymmetry that we see here. Side-to-side asymmetry that we see here. And furthermore, no single Lewis structure for ozone describes its bonding, since the bonds are neither going to be single nor double bonds. Rather, they're going to be something in between. And if we continue looking down here at figure 16, resonance structures are typically represented by drawing the two or more individual electron dot structures that are possible, and then you just use a double-headed resonance arrow that we have here, which indicates that both of these structures are actually going to be contributing to the resonance hybrid. And note that the straight double-headed arrow is only used for resonance. Now, just to ensure that there's no ambiguity, I'm just going to go ahead and sum up here. For resonance does not mean that the structure is actually going to spend some of its time in this form and it's going to spend half its time in the other form. Resonance tells us that the actual structure is going to be somewhere in between these two extremes. Once again, it's going to be in between these two extremes. And moving on now, we should also note the actual molecular geometry for ozone is actually bent, and it's not linear as we depicted here for simplification, right? And however, for Lewis structures are not really meant to represent molecular geometry. Thus, the following is acceptable for the following is an acceptable Lewis structure here for ozone. Okay, let's proceed now to our next slide here. And here we are asked to draw Lewis structure for nitrate, including resonance forms. Now again, in step 1, we're going to need to, if we recall, in step 1, we're going to need to calculate the total number of valence electrons in the molecule or ion for all atoms, and we're going to add additional electron for each negative charge in an anion. So if we come back here, we're going to need to add an electron for that anion, so that'll be 1. 5 for the nitrogen atom and 6 for each oxygen atom, giving us a total of 24 valence electrons. Now, we had already demonstrated in the previous slide that nitrogen is not as electronegative as oxygen, thus nitrogen will be our central atom. And if we go ahead and we draw out the structure as such, we'll assume for the time being that between the nitrogen forms a single bond between each of the terminal oxygen atoms. Now, if you take a look over here, for nitrogen to have an octet, right, for our nitrogen here to have an octet, since it only has 6 valence electrons at this point, right, one of these oxygen atoms, right, they must use a lone pair to form a nitrogen-oxygen triple bond. And there's actually 3 possibilities, right, 1, 2, and 3. And all 3 are, and since all 3 oxygens are equivalent terminal oxygen atoms, we'll need to draw all 3 of these resonance structures where each one of these lone pairs forms a double bond with the nitrogen. Let's do that on the next slide. Now, once you go ahead and you do that, you should end up with the following structure. Notice that the connection between the atoms is the same for all 3 structures, and that the atoms have the same positions in all 3 structures as well. Okay, great. Let's proceed now to our next slide here.